Hello and welcome. The CIMH supports national meteorological and hydrological services across the region through climate services, training, and operational guidance, helping to strengthen multi-hazard early warning systems and reduce risk from climate and weather-related hazards. This session is delivered through the VLab in support of early warnings for all, and it focuses on heatwave identification in the Caribbean. We'll briefly review how heatwaves are defined and detected operationally, then work through a short case study, a Barbados heatwave from the 7th to 15th June 2023, using a practical evidence-based toolkit that includes surface observations, reanalysis, satellite products, and soundings, to show how daily monitoring can be translated into clear early warning messages. Let's start with the definition. The WMO description frames a heatwave as the local cumulative excess heat over a sequence of unusually hot days and nights. Operationally, we can translate that into three common approaches. First, a percentile definition, such as 3 or more consecutive days with maximum temperature above the 90th percentile of climatology. Second, an absolute or fixed threshold definition, like 3 or more consecutive days with maximum temperature at least 5 degrees Celsius above the climatological mean for that date and location. Third, an impact definition, which focuses on what the heat actually does, such as excess energy demand, heat-related illness or mortality, crop impacts, and water stress. The key message is that definitions can be tailored to service needs, but they must be consistent and defensible. You may ask the question, why does heatwave identification matter? Heatwave identification matters because prolonged heat episodes are becoming more frequent across Caribbean small island developing states, and impacts cut across multiple sectors, especially health, energy, agriculture, and aviation. Early identification supports better preparedness and response, including targeted messaging and operational planning. And importantly, heatwaves are now among the most consequential hazards for Caribbean small island developing states, but they're still often undermonitored compared to storms and floods. We will now summarize a simple operational workflow. Step 1 is monitor and flag, typically days 1 to 3. Over this period, you track daily maximum temperatures, compare against the 90th percentile thresholds, and flag a heatwave watch if anomalies persist for 2 to 3 days. Step 2 is confirm and diagnose, days 3 to 5. During this time, use diagnostics to understand what is driving the heat. Synoptic and analysis charts for ridging and subsidence, sea surface temperature anomalies for boundary layer warming, land surface temperatures for hotspots and reduced nighttime cooling, surface and 2-meter temperatures for persistence, and soundings for inversion strength and mid-level dryness. Step 3 is classify and communicate, day 5 and beyond. At this time, apply the chosen WMO line definition, issue advisories or alerts, and coordinate sector-specific messages for effective action. This is the toolkit we'll reference through the case study. Synoptic and analysis charts, sea surface temperature anomalies, satellite land surface temperatures, surface and 2-meter temperatures, and soundings. The goal is not to rely on one dataset, but to build a consistent story from multiple lines of evidence. Here's the case study context. Barbados experienced an early summer heat episode from the 7th to the 15th of June 2023, marked by sustained daytime heat and persistently warm, humid conditions that elevated heat stress over multiple days. The event was shaped by a combination of atmospheric forcing, including subsidence and enhanced stability, and oceanic background conditions, with warm surrounding waters supporting a hotter, moister boundary layer. What made this episode particularly notable is that hazardous heat developed despite strengthened tradewind ventilation. In other words, even with increased flow, the atmosphere remained configured to retain heat and moisture near the surface, limiting relief and creating conditions favorable for dangerous, long-duration heat stress. From the synoptic perspective, a high-pressure system dominated, and by extension low-level divergence was prevalent across Barbados and the region. The overall pattern isn't unusual climatologically, but what mattered here was the positioning. The high-pressure center propagated westward and southward compared to its typical location. That shift implies stronger subsidence closer to the eastern Caribbean, supporting warming and suppression of rainfall. Here we're highlighting the mean temperature anomaly structure during the event. Note the vertical profile of anomalous warming from 850 hectopascals to 250 hectopascals and where the strongest warming is occurring, because that helps us infer processes like subsidence warming and stability changes through the lower to mid-troposphere. Interpreting the mean temperature anomalies, we see anomalous warming throughout the layer, with a peak signal near 700 hectopascals. The vertical pattern, warm anomalies extending upward, supports subsidence-related warming and enhanced stability. We also had a marine heatwave signal, with the sea surface temperature anomalies during the event averaging plus 0.9 degrees Celsius, meaning the ocean likely contributed extra heat and moisture to the boundary layer. That combination increases sensible heat fluxes and raises the baseline for heat stress at the surface. Now we bring in satellite land surface temperatures using NASA Worldview. LSTs helps us identify hotspots over land and assess whether surfaces are retaining heat, especially where reduced cloud cover and dry conditions allow stronger daytime heating. This image depicts LSTs on the 27th of May, about 12 days before the event. At that time, cooler LSTs can be observed mainly over the central parts of the island. This second LST image reinforces the same idea: spatial patterns matter. Even if station temperatures are similar, LSTs can show localized extremes, useful for situational awareness and for linking impacts to where people actually live and work. This image, which captured LSTs on the 7th of June, depicts some warming especially over central and southern parts of the island. Next, SST anomalies, again using NASA Worldview. SST anomalies are a key boundary condition. Warmer waters support a warmer and often more humid marine boundary layer, which can elevate nighttime heat stress and worsen apparent temperature. Leading up to the event on May 27, positive SST anomalies began to dominate the region. Here we emphasize both persistence and the increasing spatial dominance of positive SST anomalies. For operational heat monitoring, we look for coherent warm anomalies that expand and intensify, because they can sustain elevated heat stress for multiple days. By the beginning of the heat wave, positive SST anomalies were clearly dominating much of the surrounding region. In a Caribbean context, this naturally raises two questions: is a marine heatwave a precursor to a heatwave event? And more broadly, can large-scale drivers like El Niño shift the background conditions in a way that increases heatwave likelihood or intensity? Soundings help diagnose the structure of the lower troposphere, especially inversion strength and dryness above the boundary layer. Here the focus is on indicators. The potential temperature jump between 850 and 700 hectopascals is on the order of 5 to 13 Kelvin, consistent with a pronounced inversion. Relative humidity at 700 hectopascals is quite dry, around 38%. And the potential temperature near the inversion top is roughly 313 to 316 Kelvin. Put simply, warm, moist air near the surface capped by drier air aloft increases stability, limits cloud development, and supports prolonged heat. As we examine the mean wind speed structure, the key is to compare conditions near the surface with those in the lower free troposphere. What's notable, and consistent with this case, is that stronger easterly trades aloft do not necessarily relieve heat stress at the surface. When subsidence and a strengthened inversion create a stable cap, heat and moisture can become trapped in the boundary layer, limiting vertical mixing and suppressing cloud development. The result is a situation where the atmosphere is well ventilated above, yet near surface temperatures and humidity remain elevated, sustaining high heat stress. Moreover, while heat waves are often framed as calm, stagnant surface conditions, the larger-scale circulation can actually strengthen the flow both at the surface and aloft. Under a dominant ridge, subsidence, increased stability, and a tightened pressure gradient can enhance the trade wind regime even as near-surface heat stress remains high because the boundary layer is capped and vertical mixing is limited. During the June 2023 event, a strong subtropical anticyclone was positioned just north of the eastern Caribbean. As the ridge intensified, the pressure gradient between the subtropical high and the intertropical convergence zone increased. This supported stronger easterly flow at the surface and accelerated easterly trades in the 850 to 700 hectopascals layer across the eastern Caribbean. Despite this, a warm, subsiding, stable environment was maintained aloft while heat and humidity persisted near the surface beneath the inversion. Regarding the Saharan air layer, during this heatwave, SAL influence appeared minimal to moderate for much of the period. That means dust was likely a secondary modifier rather than the primary driver. While SAL outbreaks can enhance mid-level dryness, strengthen stability, and reduce cloudiness, thereby supporting stronger daytime heating, the broader persistence of this event was more consistently explained by the subsidence inversion regime and warm underlying ocean conditions. In short, SAL may have reinforced favorable conditions at times, but it did not dominate the signal across the full event window. To summarize, this was a prolonged extreme heat episode lasting at least 9 days, with temperatures exceeding the climatological 90th percentile. Persistent subsidence helped trap heat and moisture in the boundary layer, so surface heat stress remained elevated even with strengthened trade wind flow. Positive SST anomalies around Barbados provided a warmer ocean boundary condition, supporting higher near-surface temperatures and humidity. Finally, a sharpened trade wind inversion, together with relatively dry mid-level air, reinforced stability, limited deep mixing and cloud development, and reduced rainfall, allowing the heat to persist. This case study was presented as a practical, multi-source guideline for identifying and diagnosing heat waves, from detection, threshold exceedance and duration, to attribution, synoptic setting, SST, LST signals, and sounding base stability. In real-world operations, however, the strength and combination of these signals can vary by island, season, exposure, and local climatology. For that reason, indicators should be interpreted in context and, where possible, cross-checked against observed impacts and sector needs, with professional judgment applied when issuing watches, advisories, or alerts. I'd like to acknowledge the technical support provided by Mr. Chavez Pope and the review and coordination support provided by Ms. Kathy and Caesar. Sincere thanks as well to the VLab team supporting early warnings for all, for facilitating this activity, and to regional colleagues across the Caribbean who continue to advance heatwave monitoring, impact-based forecasting, and early warning services. Thank you for your attention.